Okay, dah okay.
All right, so at least 2 or 3 pun dah okay. Right, yang tak boleh is okay, but at least saya tak tengok just blank screen ya. Okay, let me see. Why do I pin myself open? Okay, let me bring this. Okay, speaker. Okay. Gallery. Spin. Okay, now. All right, can you see? Can you read?
Yes, Prof.
Gini-gini je saya nampak. Ya, on video tu gini-gini je saya nampak. Okay. Okay, so today I'm going to start with this while waiting for you to finish trying. Rasanya tak sempat buat lagi kan, the whole of chapter 5 exercises. You have to try all, go through the whole chapter of chapter 5, right? And go through all examples like I mentioned yesterday and do all exercises. Although it's not handed in, I assume that you have to try and do all. And if you have any problem or any question at all, and in any time of my class, you can just raise your hand or chat that you have question on a certain number, yeah? So we can go through during the class. Okay, I have to start with chapter 6, which is algebraic structures and groups. For those who are also taking modern algebra, or you have taken, or you are taking, you probably will see this, have seen this, okay? So to you, probably it's the second time you will see it, or just a review for you, that's your advantage. But I won't assume that all have seen this, okay? So I will start from the beginning. So first, we have to look at the the definition. What is a binary operation? Yeah. Okay, we have to have a binary operation. Binary operation means that you have a pair of elements, that's why it's called binary, and you map this element to get only one element. Okay, so that's a binary operation. So it's a well-defined function. So if you have f is a function, baru tadi quiz function kan, from a set A cross A. So this is a pair, right? A pair, a direct product or a pair from A to A to A. Okay, it has to be the same A. A is any set, non-empty set. So if you have A and B in A, and you do some operation. Okay, so the star is the operation. And this has to be back in A. Okay, we will call this also as A is closed under this operation. Okay, close is not the English close. Close means you take this element, you take another element, and then you multiply, and then it stays in the set. That is what it means by close. Example, you have integer, right? A is a set of integer, and then you have another integer. The operation can be addition, right? A plus B, integer plus integer is another integer. So we say the set of integers is closed under addition. Example, yeah. Z is closed under addition. Z is integer. Z is also closed under multiplication because integer times integer is integer. Now I want someone to give me an example of a set in which the operation is not binary. It is not closed. Can you give me an example? You can type there, or you can just turn on your mic. Meaning you have this element in the set, you have this operation, but when you do that operation, the resultant is not in the set. Anyone? Z is not closed, Z plus, yeah, I put positive integer is not closed under subtraction. Positive integers, they are not closed under subtraction. Because I take a 2 and then I take a 3, right? 2 minus 3 is not positive. That's an example. Okay, yeah. And division, yeah? 2 because 2 and 3. Don't choose 4 and 2. 4 over 2 is 2, which is still integer, right? So choose something that makes it not integer. There are many others, all right? Okay, that is what it means by binary and close. Okay. I have some examples in the, not sure if it's already in your e-learning or not, the notes, but I have some examples in the notes. Hannah, is Shiham here?
Yes,
okay.
Yes,
They will get the notes, yeah?
Yes.
Okay, so I have some other examples in there, okay? And this might not be only limited to numbers, okay, and integers, because sometimes our function or mapping can be not numbers, they can be like matrices, okay? So depends on the question, okay? If you have matrix, maybe you cannot multiply matrix, so it's not an operation, something that you can do. What if the operation is, sometimes they write like this, x, a function f is defined as, I have never given this example, f is the child of, maybe I don't put f yet, I put a mapping, yeah? I put a mapping. What do we call a mapping? The original, the normal mapping, maybe, okay, the child of. So if you have this person here and this person here, okay, if this is the set of parent, it's not a function, because you, let me put your name. Siapa ada kat situ? Apa silau sangat saya ni? Alia, Nur Alia Zulkifli. Kita letak nama Alia di sini. Alia ada 2 Alia kan? Fatana, Fatana. If I put parent here, Alia, you are the child of your dad and mom, right? So I will have like this, which is not a function because we cannot have 2 images, right? So if I put this as only the mom, mother, yeah? You have only 1 mother, kan? Mana ada orang yang 2 mothers? I mean, the one that give you birth, all right? So dalam ni tak ada adik-beradik, say Alia and Fatana adik-beradik, adik-beradik dalam kelas lah, right? So say you are sibling like I'm your mom in this class, okay? So you will have this, yeah? Can? It's okay to share mom because a mom can have more than one daughter. Okay, so this is a kind of example that does not involve the numbers, but this is just a function. Okay, you can have another boy here, right? And you have different mothers. Maybe some mothers, they don't have a child, it's okay. But all of you have mothers. How can you not have a mother and you are here on earth? Okay, that is a function. Nice, quite nice. But what about the operation? How do we define this operation? Susah kan? Operation apa? You have Alia operation star tu apa? Maksudnya operation pegang tangan ke, ketuk kepala ke? That's not kind of operation. So we don't normally do this for this example as the operation, yeah? Okay. Next, so you have to look at all the different examples, not only from my notes, but also from references. Try to get some books, okay, to see all kind of references, because there are so many. Like we have Q, right? Sometimes it's not close under this for Z under division, but this question just now, go give me one, right? Go. What about this? Is Q close under this? Yes or no? Cepat jawab.
No.
Why? You have 2/3. You divide like 3/, not 3, like 2/7. Oh, tak naklah yang sama. Something like this. This is 7/6. It's still Q. Why not?
Oh. Oh, then yes, so.
Cepatnya tukar soalan. The answer is still no. But I didn't give you the counter example, the right counter example. Under division, okay, if zero is a rational number, right? So you cannot divide by 0. So that means it is undefined. Okay, you have to think a little bit. This chapter is a little bit different in the sense that you have to think first before you just give the answer. It's not straight away calculation. You have to think first. Yeah. So if I ask you something about the plus which has, if I give you something like this, the answer would be yes, because 0 is not included. So you will say like A/B divide C/D is actually A/B times D/C, right? Which is AD/BC. B and D cannot be 0 because it's in Q, and this is all positive. So you cannot divide, and A and C cannot be 0, okay? AC cannot be 0 because it's Q positive. BD cannot be 0 because in Q, that is how it is defined, right? So A, C, B, D, they're all not 0. So this is not 0. And this is okay. This is not 0. This is all positive, right? This is all positive. So the question can change with the same operation, but a different set. Or with the same set with a different operation. Okay, so you have to go through as many and understand why it is a binary operation and why it is not. That is number 1. Okay, now you have to know also some properties of binary operation. Okay, I have mentioned this in the previous chapter. So you have to know about a commutative, right? In the binary operation, you have to know about commutative. You have seen or hear this so many times, right? Commutative means AB is BA. For all AB in the, say, I call the set maybe A or the set S. A, ya, tadi A kan. The second one is you have to know about associative. When I put AB, there is actually a dot in the middle, or there is actually a star in the middle, in which it is an operation, not necessarily multiplication. It can be plus. Yeah, it can be plus, it can be multiplication, it can be composition for function. So your A can be continuous function or polynomial. Okay, they can be different. See, associative means ABC is ABC. There is a dot here, yeah? I didn't put that. Okay. As before, we have seen this idempotent, right? It means A times A is A. Okay, if you came through this, then you can see all examples also. Okay. Next, identity. Sometimes we write this algebraic structure as this. Algebraic structure as some book write depends, yeah. The algebraic structure, the set and the operation. Sometimes algebraic structure has more than one operation. Later on, if you take ring has two operations, plus and multiplication. Okay, so identity, if you have this algebraic structure, then we say I in S is an identity if A dot I is A and I dot A is also A for all A in S. This one is there exists. There is one element inside that set in which when you do the operation left or right, it stays the same. Okay, A stays the same, right? Okay, now I will give you a set and operation and try and give me the identity. Okay, so I will give you the set and the operation. You think, and then you give me the identity. Sometimes a book, they use E. Later on in a group, normally we will put E as the identity. Okay, Z under plus, because it's binary, right? Integer plus integer is integer. What is an integer? Give me a number, an integer, in which when you add A to that number, you get A back. It won't change the number. What is the I? Okay, Alif dah jawab. Okay, 0. Because A plus 0 is A. Right? A plus 0 is A. Or 0 plus A is A. That's the identity under addition. This also close under multiplication because integer times integer is also an integer. Okay, what is the I? What is A times I is A? 1. Okay, that is the I. Okay. If you have like Q numbers, they're all similar. If the operation is addition, then it is a binary. Close is always 0. Okay. But if it is multiplication for a number, and the multiplication is always 1. I can change the operation. I can say, suppose S is Z, and this operation on the set AB in S is defined to be AB plus A. AB plus A. This is an integer. Multiplied by integer is an integer. Plus another integer is integer, right? So this is close. Okay, this is close. It's a binary. Now I want you to find I. This is not the normal one, right? This is not the normal operation. Give me the I. How do you find it? Meaning A star I, this is similar to, let me write as usual, yeah. A star B is this. Try to find the I. Siapa dapat? Anybody? So you will use this formula. A star I is A. I star A is also A. And you use this formula. This gives A times I plus A is A. This gives A times I is 0. I can be anything. So this gives I is 0, right? Because A can be for all A, right? This is for all A. For all A, B in S. This is for all A, right? For all A. This is also for all A. This is a simple algebra, right? Buang A and 1 minus A both sides, AI 0. If for all A, I has to be 0. But you had to satisfy also this one, not only one side, it has to be both sides. Let's check. So this gives I times A plus A is A. I times A is IA plus A. IA plus A equal A. So I times A is 0. So again, I is 0. So although the operation is different in this case, also the operation is different. In this case, I is still 0 because of this, but you have to show this by definition. Okay, all right. Okay, and I give some example. Another one that I want to add here, a definition is about the inverse. Gelamping saya bukan sebab saya kontak rapat atau positif. This is just siapa balik luar negara memang kena pakai gelang. Jangan viralkan. Okay, so inverse, yeah. Inverse. We say about inverse only if the I exists. Okay, so if there is no identity, there is no inverse. All right. So that is the first rule. Now, inverse means if the inverse exists, yeah, okay. Y is the inverse of X if Y dot X equal X dot Y equal the identity. Okay, that is the definition of the inverse. And normally the inverse is written as this X to the negative one. Okay, X inverse. That is how we write that. Okay. So the question is, you will be given a set, you will be given an operation, and you have to show or decide whether all the properties that I just listed just now, yeah? So let's go to one example. How long do I have? Okay, still have half an hour. Before that, any question? Okay, tak ada jawapan, tak ada soalan. All right, good. Okay, so this is an exercise given in the notes. Let star be defined as A star B is 2AB in R, yeah? In R. AB in R. So the algebraic structure is actually R and star. Real number, yeah? Real number. A star B is 2AB. Not the normal A, just AB. The first one, star is commutative. Easy, right? Because A star B, you want to show this to be B star A. So it's 2AB, which is 2BA, and 2BA is actually B star A. B star A will be 2BA. If you are not sure how you can switch over here, you will write A star B is this, B star A is this, then this is equal to this, is also okay. But the intelligent way is to start from the left, do something, and stop on the right. You want to show A star B is B star A. It's also associative. This is just like a normal operation, multiplication, only you have 2 outside, right? Okay. Now find the identity. You want to find I in R such that A star I is A, which is I star A. What's the answer? What's the answer? Anyone? A star I is 2 times A times I, right? We want it to be equal to A. Okay, this gives, potong-potong kan? 2I is 1, imply I is a half. And you do the other side also, you will get the same because this is just numbers commutative. And you can check if you replace I by 1/2, you will get A, right? So in this case, I is a half, but you have to do the other one, the other side. So, okay, next you have to find the inverse. To find the inverse. Oops. Okay, find B, which is A inverse, such that A times B is a half, which is I, right? Okay. So what is AB? AB is 2, AB is a half. you want to find B, right? B is 1/2 divided by 2A, which is 1/4A. Betul ke ni? Try lah kalau tak sure. So A start 1/4A. Check ya. A star 1/4A is 2A 1/4A. A star B is 2AB. A star 1/4A is 2A. Okay, then right, a half, which is the I. Okay, then you do the other. Pelik sikit kan, but this is the inverse of A. So A inverse or B is equal to 1/4A. And this is also in R, but there is a but. There is a problem, right? There is a problem. What's the problem? This is not for all. Okay. But not if A is 0, right? Yeah, except 0. Because 0 is also a real number. That's the problem. If there is multiplication involved and the inverse somehow was 1/, right? Then the one in the denominator cannot be 0. Like 0 inverse is 1/0, undefined. So because of the 0, there is no inverse for all elements of this set. So we say the inverse does not exist for all elements in the set. The inverse does exist for all except for 0. So in general, we don't have the inverse for all elements in the set. Okay, this is very important, especially when we want to show or decide whether a set is a group or not. Okay. Okay? Okay? Apa jawapannya kalau saya tanya okay ke tak? Okay. Saya tukar view sikit. View gallery sikit, ada yang tak okay ni. Okay. Ada gini juga kan kalau tak okay. Jangan cuba kalau ini betul tak okay. Alright, so I move on to the first definition of semi-group. Before we go to group, we have semi-group. Okay. Semi-group. Okay. Let S be a non-empty set. If it's empty, what's inside, right? So we don't want it to be empty. And this is a binary operation on S. Somehow, some books, they can probably just write differently, different sentence, but at least the point is there. It has to be non-empty. You have to have a binary operation. If star is associative, then S with star is a semigroup. Okay, so very easy, right? Associative. Easily we can write some example of semigroup to be Z plus associative, right? Z cross matrices under addition and also matrices under multiplication. I put n by n because if m by n, you cannot multiply, right? M by n, n by m. You probably cannot multiply, but this is just to be safe, square matrices. Matrices are associative. You don't have to show because you have taken it in linear algebra. We have seen this in linear algebra. This one also, and many others. Okay, these are all semigroups. These are all semigroups. The notion of semigroup have been used very, very widely in many research, not necessarily in mathematics, sometimes because we can do also modeling. So the real life situation, which is modeled through mathematics, using symbols and others, sometimes we want to show that it is a semigroup that satisfies certain property. Okay, you might be doing this later, right? Maybe in your undergraduate project, not necessarily under pure mathematics, but some others can probably need to show something as a semigroup. Okay. Now, we want to check whether a semigroup has an identity element or not. Okay, so probably you are given a set, and then the first question is, show it is a semigroup. The second one is find or decide whether there is an identity element. Okay, and we have seen like before, if it is a plus 0, right? If it's normal operation, if a multiplication, there is a 1. So you know, if I change this to like this and like this, okay, if I change this, the operation is still associative, right? Because the operation does not change. Okay, if it's positive integer plus positive integer is positive integer. Positive integer multiplied by positive integer is positive integer, right? Okay, but the I here, if you want to add two integers, a plus what equals a, it has to be 0, right? Under addition, but 0 is not in here. So when I didn't put this, the I is there, the identity. When I put this, the I is not there. The same thing if I put Z minus. This is still binary because negative plus negative is more negative, right? And what about this? I didn't put this earlier, but this is not binary, right? Because negative times negative becomes positive. So it's not close, right? So you don't put this under here because it's not even close. So you have to try to put some examples. if many examples that you put work, doesn't mean it works, right? Like just now, if you put the rational number, and then you say this rational number multiply or divide rational number is a rational number, but there is only one, 0, that does not work. So you have to think about positive, 0, negative. If it's in the set, you have to think about this. And if it's R, you have to also think about fractions, because fraction is in there. And sometimes you have to think also, if it's R, about the non-rational number, because it might not work for the irrational number. So infinite set, it does not cover all. You cannot list everyone, but you have to think about this. For this one, yes, the identity is still there, right? Because it's 1. If the question is about this, it's not even, because it's not even binary. Okay. All right, semi-group plus identity, that is another name. Okay, the name is monoid. Okay, this is semi-group and identity. The name is monoid. And I have listed some monoid before here, right? In the example, like Z with plus is a monoid. Z with multiplication is a monoid because it has identity. And if I put Z plus with addition, it's not a monoid because the identity is not in. Okay, so the question might be just simple. You're given a set, you're given an operation, decide whether this is a monoid or not. Decide whether this is a semi-group or not. Okay. In my notes, I have homomorphism versus isomorphism, but I want to hold on to that later. Till later, because I want to finish this with groups, yeah? Okay, now for groups, a group is a monoid plus inverse. Okay, monoid plus inverse. So an example is still this. Because first is close, right? Second is associative. Third, there's an identity 0. Fourth, for A, what is the inverse? A plus what is 0? A plus what is 0? A plus negative A is 0. And negative A is also an integer, right? So there is an inverse. Yes, this is a group. Okay, you have to go through. Closed, yes. Associative, yes. Identity, under addition, yes, 0. And inverse, okay, is the inverse, the negative. What about this? Let me give you 2 minutes to think about this. Is it a group? The answer is easy. Is if it is yes or no. 50-50, yes or no? Emilia, are you here? Emilia Eliza.
Yes, Prof.
Yes or no?
I think yes.
Okay, first, this is close, right? Integer times integer is integer. Okay. Associative, right? A, B, C and A, B, C. Multiplication. What is the identity? What times 1 is A times A times identity is A, so the identity is 1.
1.
Okay, what is the inverse of 2? 2 times what is 1?
1/2.
Okay, 1/2. What about 1 negative 2? What is the inverse? Negative 2 times what is 1?
-1/2.
Negative 1/2, okay. What about 0? What is the inverse? 0
No
times
inverse.
what? 0 times what is equal to 1?
No inverse.
No, right? So no, because 0 has no inverse. So like that's why just now I said you have to check also not only the positive or negative, but you have to check for 0. Yeah, so the answer is no. When you write out your answer and reasoning, okay, you have to think first. Don't just write from the definition. You just go because your answer is, the reasoning is only this. Even if you do 1, 2, 3, you're just wasting your time. There is no mark. The mark will be just no, because it has no inverse. 0 has no inverse. So think first before you write anything, because your answer only for that particular one. But if it is like this, if it is, you have to write all. Yeah, 1, 2, 3, 4. If it is not, just go straight and find and think first and find what is not. Okay. All right. Later you go through the examples and think. Don't just read. Look at the set, look at the operation, and then think. Go through one by one and think, and then compare. It's okay to make mistake. Then that will help you to understand more and to remember more. It's okay. Amelia, I'm sure after this, you will remember this moment that you give a wrong answer, but hopefully I sure you will understand more about why it is not. Betul tak? Yeah, Amelia?
Betul, Prof.
Okay, next I want to show the Kelly table. Okay, I will stop at 12:40. Supposedly the 50 minutes kan kelas plus 50 minutes. Okay. Okay, semua orang kena doa-doakan juga ya, result saya negatif ya. Okay. Right, Kelly table. Okay. Kelly table. Let me ask you this. Who introduced Kelly table? Kelly, that's what the name is, Kelly table. Okay, Kelly table has rows and columns as elements in the group. So Kelly table is a multiplication table. Kita belajar itu kan multiplication table, but for a group. So Kelly table give us a multiplication table. Let me call it maybe A, B, C, D, A, B, C, D. in which every row and every column has only elements of the set or of the group, no other, no outside, right? So if you see, this is actually the element of the group. We normally call it Z, okay? Since the binary operation is closed, when you look at a table, if the element inside the table are all just A, B, C, D, it is closed. But if you see in the table, somehow there is an F, right? Or G. Then meaning is not closed, right? So the elements inside the table show us whether it's closed or not. I will write it like this, A, B, C, D. A, B, C, D. Macam kita main apa? Yang satu row or column has to have only one number or one letter. Main apa tu? Sudoku ke apa? Okay, so if it is a group, every row or column has only that letter once. Okay. Okay, there is already the A here, I put B here, I put B here. Okay, there is already A here, so I put A here. A, B, C, D. This is not unique, yeah? There's A here, I put A here. Okay, A, B, C here, C here, D. It's not unique. I can do another one with this A, B, C, D, but different, right? And still a group. Okay. The row or column that is similar to the header or the one on the left shows us the identity. Okay, shows us the identity. Mana identity? Which row? Which row? First, second, third, fourth? This row, right? This row is the same as the top row. As similar, this column is the same as that column, which shows this is the identity. Okay, I is the, B is the identity. If you're not sure, you can try. A times B is, so you read like this, A times A is B, A times B is A times C is D, A times D is C. So if I say I is, B is the identity, you can check. If you multiply B with A, this is identity, right? You got A, right? Right? Then you change this, you change this, you change this. The I you don't change. This should be B, right? Okay. This should be C. Yes. This should be D. Yes. And the other way around. That's why we get another one, which is equal to BA. BA. Okay, and then BB still BC, BD. That's why it's this. Okay, BB, BC, BD. Okay, that is to find the identity row that is the same as the top one. So easily you can see it. So that means it's not always the first one is the identity. Okay. Next, you want to find the inverse. If it's already, there's already the identity there, how do you find the inverse? Is you go to the every row and you find the identity. The two column and row that intersect, that is the inverse of each other. So the inverse just now is B, yeah? So you find B, okay, for each row, and the corresponding element is the inverse. Okay, so for the first row, A is the inverse of A. For the second one, B is the inverse of B. For the third one, C is the inverse of C. This is a unique example. It's not necessarily the same. And D also, right? D inverse is D. Okay. Okay. Belum okay. Tengah menyalin. Okay, Alia kata okay. I will change. I will give another one. Boleh padam tak? Boleh? Okay. Senang je kan? Boleh screenshot, simpan. After this, you can watch the video. Okay. Last one ya. I don't want it. Okay. What is the A? A. Okay, saya try je lah. Jadi kita A, B, oops, C, D, right? Okay. A tak ada lagi. A, B, right? Okay. A, B, C, A.
Prof C.
Boleh. Apa dia? Ada B dah. C ya. Okay. B ya. B, A, B, C, D. A, B. Okay. Okay tak? Okay. Try to find the inverse and the identity. Okay, so what is the identity?
A.
A, yeah. Okay. Then I put A inverse, B inverse, C inverse, D inverse. So what I do is I will circle A. A is the identity. Okay. So A inverse is A. B dengan C, BC and CB, they are the same. So if B is the inverse of C, terbalikkan C is also the inverse of B, right? Because we have, if Y inverse is X, take inverse both sides. Inverse is go back. So if Y is the inverse of X, X is also the inverse of Y. Okay, so D, tinggal D, D and D. Okay. Okay, last one is I want to talk about a billion group. Last one, yeah. A group G is a billion if it is commutative. A group G is a billion if it is commutative. Meaning? xy is yx for all xy in G. Okay, meaning xy is yx for all xy in G. Okay, so if they are just the set like integers, the set like numbers, okay, they are all abelian group. But if like matrices, they're not abelian under multiplication because AB is not BA, right? Under addition, yes. Okay, so what you had to do, I still owe you the homomorphism and isomorphism. I will continue that in our next class. But what you can do now is to go through the chapter. We still have some more like subgroups, cosets, that is for next week. Then we have normal subgroup. Okay, so I have like 2-3 items left for this one. You can start first, but you have to finish the chapter before chapter 5. Then you can start with chapter 6. All right.